Okay.
The action. Uh, I'm very happy to see you all. Thank you for coming at this moment. And what I've learned recently that there is a phrase in Brazilian Portuguese which is a vida não é a morango. And it means that, well, you cannot have cake and eat cake at the same time. And my problem for today's talk is really that during my two previous talks, I had always one more talk. So I could postpone. Oh, okay, if anything went bad or not according to the plan, I could say, okay, I will tell about this next lecture. And guess what? This is my last talk, and I do not have this opportunity anymore, and this creates problems, serious problems with what I'm going to tell you today, because apparently I won't be able to tell you everything which I would like to, so we have to make a pact that if you, in some sense, will be interested in the stuff, then you will later either ask me or check the notes, which I hope will be created after this course, or in any way you will continue your studies. And let's see what we are able, where we are able to get today. So, okay, I can tell you where we were so far. So we have this notion of reduction between equivalence relations on Polish spaces. And this notion tells us that one equivalence relation is simpler to solve or as hard to solve as the other equivalence relations, meaning that it is as hard to answer a question about whether two objects are equivalent according to this relation as for the other relation. So E is Borel reducible to F. This means exactly that. So now we know that if we can reduce one relation to the other, and if the first one is not Borel, or not Borel, if this is not a Borel set actually, that should be written here. So if E is not a Borel set, and in Borel reduces, I think I use the notation of this kind. So if there is a function which reduces, okay, the one set to the other, so we have a reduction between equivalence relation, and we also have a notion of reduction between sets. So for a set A contained in the space X, B contained in the space Y, we say this, that A is Borel reducible to B, even only if there exists a Borel function, let's call it psi this time, such that X is in A, even only if psi of X is in B. So if we want to use the second kind of reductions to prove that some equivalence relation is not Borel, then we need to find a set which is not Borel and reduce it in terms of finding this Borel function to our equivalence relation. So everybody's favorite non-Borel set is obtained in the following way. You start with the vertices of the full tree of infinite order. So this is really the full tree. You have infinitely many children for every vertex, and you put an ordering on this set of vertices in such a way that in this ordering, a parent of every vertex appears earlier than any of its children. The ordering is not important. One ordering of this type always, at least one ordering you can always find. And then with this ordering, you can put the product topology on the set of all characteristic functions telling you whether you take a vertex or not. So 0, 1 to the v is the set of all characteristic functions on the full tree of infinite order. And all characteristic functions, they pick really among the subsets of vertices. They tell you whether a vertex is in the set or not. But we are really interested in some subfamily of these characteristic functions. We are really interested in the family of characteristic functions which gives us subtrees. So what is a condition for a set of vertices to give us a subtree? A condition is very simple. If I see a vertex in this set, then its parent also should be there. And this, if this set is non-empty, then we have our collection of subtrees. So trees is the collection of all tau in 0, 1 to v such that tau is non-empty and v in tau implies that parent of v is in tau. Parent of v is in tau. So no children are left unattended in our set. So this is, with the topology we have chosen for our space, this is a closed subset. There is no dynamics on this subset, but this gives us a special subset of all characteristic functions. And only for our better intuition, we can picture this set as the set of all subtrees of the full binary, of the full tree of infinite order. But this is not necessary. As you can see, you can state all these definitions in the purely combinatorial way. And then among all trees, I pick one family. So there's a definition of a path. A path is a sequence of vertices. Now, UN is not the number in this ordering. It's just an index for some sequence of vertices with this property that it is the other way around. I'm sorry. That every next vertex in the sequence is a child of the previous one. So path is simply a sequence of vertices which we can picture on our full tree of infinite order as a path going from the root to the leaves. And now, we have this family of ill-founded trees. So this is the family of all trees which they have, that there exists infinite path in tau. So this is the family of ill-founded trees, and this is an example of a non-Borel set. Okay. Let me still thank the Maglies for a remark that we don't want to take the complement of the set of ill-founded trees, but rather we prefer to consider ill-founded trees as a subset of the family of all trees with unbounded depth. So every tree has associated a natural notion of a depth, which is the length of the longest path from the root to some vertex in the tree contained in the tree. Okay? So there can be trees. So of course, every ill-founded tree has an infinite path, so it has unbounded depth. But here, the point is that because we have trees with infinite order, there can be trees without unbounded path, infinite path, but still of unbounded depth. Arbitrarily, we can go arbitrarily deep. And this family is nice because it allows us to do some constructions and continue them, and only at the very end we decide if the tree has unbounded depth because it has an infinite path, or because it is just a tree when all paths are finite but arbitrarily long. So we consider the set of ill-founded trees as a subset of this set. And this is still a situation that we have a Polish metric space. This is still Polish metric space. And this is still non-Borel subset of this Polish metric space. So now the whole goal of many, or the whole solution for many classification problems goes as follows, that you construct a map I don't know how to call it, maybe capital Phi, from the space of trees to the space of systems. And the space of systems depends on the actual classification problem you would like to produce, such that for example, you produce the following: that the image of an image of a given tree is isomorphic to the inverse of a given tree. We consider only invertible dynamical systems from some family. And you do it even only if your tree is ill-founded. So what you really achieve by this, if you are able to find a Borel map of this kind, you are actually able to show that that your problem of isomorphism on this family of systems is not Borel. Because given a tree, you produce actually always a system, but okay, if you produce the system and you can reverse the system, you in fact produce a pair of systems, right? And if you produce a pair of systems, then you are now mapping from the set of all trees into the set of all pairs of your systems, in this sense. And you achieve that if your tree is ill-founded, then you obtain a pair which is isomorphic, which really means that you are reducing the set of ill-founded trees to the set of pairs of your systems which are in your equivalence relation. Okay? This is a scheme which has been used many times historically, and I don't know, I don't really know if there's any other so far variant of this method. Okay, there are variants of this method, but they do not change this basic principle, that this is what you more or less do. Then in order to prove that your favorite isomorphism relation on your favorite family of dynamical systems is not Borel, you construct exactly a map of this kind. And this is the moment when dynamics enter the picture, because you may want to, okay, maybe I a little bit exaggerated in the sense that this method has been used in all situations in which we don't have a better information about how badly impossible to solve is our equivalence relation, because there are other methods in which we can also conclude the similar result. But this is it. So in order to spend like a little bit of time still on showing you how, and this method, okay. So in order to spend a little bit of time to show you how this method works, I will consider a special case of using this method, which will be the following way. We consider C or Kent. This will be our a counter set, counter space, counter set. So there are many counter sets, but there is only one counter space, meaning that all counter sets we encounter are really homeomorphic to each other. So we can really take as a model for our counter set, we can take the space of all one-sided sequences, but once we picked our counter set, then we can consider the space of all B-infinite sequences of elements of this counter set. So we take elements of the counter set and we put them into B-infinite sequence. And if we do that, then we can picture this space as the space of 0, 1 sequences and we can consider each 0, 1 sequence as a column in a B-infinite matrix. Right? So I take now elements of my counter sets and I put them in a B-infinite sequence. I obtain two-sided sequence, but each of the element in my sequence is now another sequence. So I picture this sequence as a column. And I obtain this is a picture of typical element of this space. And funny thing is that this space is still counter with the product topology, that this is still counter space. So we just got a very sophisticated representation of the counter set, but we can still, this space is good because now we can introduce dynamics. That's the first moment when I ever even been to the dynamical system conference, when the dynamical systems appeared more or less at the middle of the third lecture of the mini course, but okay. So you see how much I'm late with anything interesting. But now on our space, we can introduce dynamics. And of course, when we introduce dynamics, we are lazy. We do it in the simplest way possible, so we just introduce a shift. We take our matrix, and we shift every column one position to the left. And this is the whole dynamics we introduce on the space. Now, of course, we can have the space of subshifts or shifts which is now the space of all x contained in our counter set to the power z, such that they are invariant under the action, non-empty, and closed. So this is the space of our dynamical systems, but then we can still consider the space of minimal subshifts, which is the space of y's in the space of shifts, such that y is infinite and y is minimal as a dynamical system endowed with this action of the shift. And in fact, this is a little bit of work, but not really much, to prove that this is the correct model for all minimal homeomorphisms of the counter set. This means that if you pick any minimal homeomorphism from a counter set to itself, then there will be an element of this set which is topologically with the dynamics of the shift restricted to this set being topologically conjugate to your minimal counter system. So this, okay, if you take any, minimal counter system. So, but this is the point, this is why we need to take spaces with infinite cardinality, because of course this space also has periodic points. I don't see Zeze, but she wanted to see some periodic points, so this space also has periodic points. Really, we don't want to consider them as the proper minimal counter systems. And again, what is the topology here? The topology in this space is given by a metric, because it is a nice space in the space of the shifts. And this metric, you first start with the metric between points in the space, and this metric measures if your sequences of columns are similar, are the same on the growing boxes of this type. If they are on a big common box, then they are closed. If they are not similar, if there is at least one element such that you look at this window of this type and they are different, then the distance is appropriately big. But this is so this is a variant of a well-known metric on the space of all sequences. But now instead of sequences we consider matrices. But this is just a change of the enumeration of elements into a sequence, in fact. And then you can prove that this is actually a G delta subset, which means that this is a Polish space with the induced topology, and now you can do your result. You construct a map from trees to minimal subshifts, which has this property that you can do it even by a continuous map, and given a map, this map, given or maybe I should make a star, here I should specify, because now we really want to consider just trees with unbounded depth. So let this space be trees with a star. So you really construct a map from trees in the star to the space of minimal counter systems, which has exactly this property that given a tree, you construct a counter minimal system which is isomorphic to its inverse. Now, inverse is very simple because you go in the other direction. Or you just flip all your columns in the reverse direction. So you get from a tree, you get a system which is conjugate to its inverse, even only if the tree is ill-founded. Otherwise, if you take any other, so you should be able to construct a minimal system of this kind every time you receive a tree of unbounded depth. Okay? And what is now your procedure of constructing the system is that you will read your tree vertex by vertex, and by this I imagine that I obtain information about my tree in a way that somebody tells me, goes along the list of vertices we have here, and tells me if the vertices are in my tree or are not in my tree. And of course, the first step is obvious, because in every tree the root has to be there. So the first information, okay, the full tree is the root is there, but then things may go in a various way. The next vertex may be there or maybe not. Then the next vertex on the list of the vertices of the full infinite order tree may be there or maybe not. And I have to adapt my construction according to this, to receiving that information. Okay? This is the way of making sure that your construction at least gives you is continuous. Because if you receive two trees for which the characteristic functions agree on a large initial segment of natural numbers, then this means that you receive two trees which are close next to each other in the topology on the space of trees. And as a result, you would like to construct two systems which are next to each other in the topology on the space of sequences, of minimal systems, yeah? And what is your topology on the space of minimal systems? Minimal systems are compact subsets of the space of all shifts. So and on the space on all shifts, you have a metric. And if you have a metric on the compact metric space, you can use the Hausdorff metric construction to get a metric on the space on all subsets. Compact subset, non-empty compact subset of the space. So this is what you do. And now a simple consequence of all those definitions is that two subshifts are close to each other, even only if you look on those subshifts through a window of this size, then you see the same patterns, right? So looking on the space on a subshift means that you look at some family of matrices. But imagine that you can only you cannot really discover the full content of the matrix. You can only see what kind of a finite submatrices you can see in your window. And if the window is sufficiently big, and for two subshifts, if you see the same content in this window, then this means that those two matrices are close to each other in the space. The set of families of those matrices are close to each other in the space of minimal subshifts. Okay? I hope this explains something. If not, then let me know. But this is how it goes. That you transfer, in order to get a continuity, you use a metric on the space of all subshifts, which tells you that two subshifts are close to each other, even only if you can find a large window such that looking at the elements in those subshifts through that window, you see only the same set of patterns. And this is how you measure the distance. And this is, and now the point is that, okay, you have to make sure that at the very end, a couple of conditions is satisfied, because now what you do is that upon receiving information from the tree, whether the vertex is there or not, you really start to restricting your set of matrices by imposing some conditions what you can see on larger and larger windows. So you do Tamara. now it would be great if you remember a lecture of Tamara, because Tamara spends much time that I have now on explaining how the language determines the shift. Which means, and here the same principle applies. If you restrict possible contents you can see in those finite windows, then you pick a subset of your space. So determining a shift means that for a growing set of windows, you put more and more conditions what you can see inside. And in the very end, and this is the moment why you actually want your trees to be on unbounded depth. Because a tree of unbounded depth will mean, in this type of the construction, then on each level, you will put, you will have something to do. So we will put more and more restrictions. And after getting infinitely many restrictions, you should get minimal subshift. But the first vertices of the tree, they tell you only what you do at the level of smaller windows, and the full tree tells you what you do everything on every size of a window. And thanks to that, you have continuity. Okay, now I'm in the middle of the lecture. So I am afraid that I have to leave a discussion of technical issues you use to get some results, and I should maybe look to the future and to the past to tell you what could be done and what has been done so far. So this technique was, I think, first used by Foreman Rudolf Weiss, not in the context of the minimal subshifts, but they use it to show that the ergodic measure preserving systems. So now I'm sorry, I no longer have time to explain everything. I have to somehow appeal to your knowledge or ask you to check the details later. So ergodic measure preserving system, the isomorphism relation on ergodic measure preserving systems is not Borel. Unfortunately, Dan Rudolph died when this paper was still in press. So later, just Benji and Matt, they continued that story, and they found a way to show the following. That, okay, here you have to put all, here the space is the space of all automorphisms of the unit interval with the equipped with the Lebesgue measure. So you consider all B-measurable invertible transformations from the unit interval to itself, which preserve the Lebesgue measure. And for such automorphism of the measure space, you have a notion of ergodicity. And you take the set of ergodic ones and you put the isomorphism relation, and it turns out to be not Borel, which means that any solution of the isomorphism problem for the measure preserving systems, even ergodic, is hopeless. The result for not necessarily ergodic systems was obtained a little bit earlier by Hjord. But of course, in dynamics, you can say always that, okay, maybe your isomorphism problem for non-indecomposable systems is hard because the complexity comes from the fact that for the decomposable systems, you can decompose them into indecomposable pieces. And the complexity comes from the permutation of the decomposable pieces, not from the dynamics itself, but how you put together your decomposable pieces into your space. Maybe this is the source of complexity. So here did it for systems which you can decompose, and I think in fact the proof was based on the complexity of the ergodic decomposition of the stuff. But now with Forman, Rudolf Weiss, which were the first one to use this kind of technique I described for you for Cantor systems, and I did it for Cantor systems because I think it is easier to appeal to topological properties than the measure theoretic ones. But the idea is the same, basically. They showed that no, the isomorphism relation is not Borel. Then Forman and Weiss, they showed that no, that even the abstraction of going into all automorphisms is not necessary, like measure preserving isomorphism on the space of conservative, so preserving the Lebesgue measure, diffeomorphisms of the two torus. But isomorphism is still not topological, but measure preserving. Right? This is still not a Borel equivalence relation. It takes a lot of work actually to translate abstract systems into this concrete space of systems. And we know more, namely, there's like a series of papers by Maglius, Gerber, and Philip Kunde, and they extend these results in many directions, and those extensions are highly non-trivial, because now I hope you can see what is the problem. That the idea for a proof is kind of simple. Well, just encode trees into your systems. But the execution of this idea is actually quite hard, because you have you have to have a very good command on the isomorphism relation among your systems, such that you have full control, right? It is like you not only have to be able to construct a family of examples parameterized by trees of unbounded depth, but you also have to have a good command over the your favorite isomorphic relations between your examples. In such a way that you have isomorphism, say, between a system and its inverse when the tree is ill-founded, and you don't have it when the tree is well-founded but has just arbitrary long finite branches. So this simplicity is now a little bit not so easy to achieve. So Maglius and Philip, so Gerber and Kunde, they extended to, I think, weak mixing systems. They obtained similar results for Kakutani equivalence. which is even harder to do because it is like a coarser equivalence relation. It is easier for two systems to be Kakutani equivalent than just measure theoretically is isomorphic. And they are always negative, so this is not Borel. Every time you show that the isomorphism relation is not Borel, which means that you always will have inherently big problems with deciding whether two systems are isomorphic or not. You cannot hope for any invariance. But if you want to do mathematics, this is also a good answer, because you know that those relations are analytic. And now the question is, how hard the problem of classifying your ergodic measure-preserving systems is among all classification problems which are analytic but not Borel. And we know that there is a maximal problem of this type, and we actually know that this cannot be maximal because isomorphism of the measure-preserving system is one of the examples of equivalence relation which comes from the group actions, right? Because this is really a conjugation on this, the space of all measure-preserving automorphisms of the Lebesgue space is actually a Polish topological group, right? And two systems are topologically conjugated if they are conjugated also in this algebraic sense inside this group. So actually, the conjugacy relation is the same as the orbit equivalence relation. So let me maybe state this. Whenever you have an action of a Polish group on a Polish space, it's like the action of the integers. We consider they are given by actions of homeomorphism. Flows are given by actions of the real line, but you can consider more general actions. So Polish action, then you can define the orbit equivalence relation introduced by this action by saying that 2 points are in this orbit equivalence relation even only if they belong to the same orbit of your action. So x1 and x2 are orbit equivalent even only if there exists G in your group such that acting by G on x1 you get x2, meaning that they are in the same orbit. But the orbit defined for group actions. So among all analytic equivalence relations, those given by actions of groups are simpler than the general analytic equivalence relations. So at least we know that we are not in the worst case scenario for our classification problems. So here is really, please, I invite you to consult papers by those authors for more details. But I have to run to another subject to give you some hints or pointers where you can go next. So here we have a lot of results, and there is also a result. A result I was discussing is by Garcia Ramos, Kasprzak, Kunde, Kwietniak, and Deka. So Deka, Garcia Ramos, Kasprzak, Kunde, Kwietniak is that the minimal subsystems on the counter space, so minimal homeomorphism on the counter space with the topological conjugacy is not Borel. So they are some results, and then they are results for the topological classifications of diffeomorphisms. So I think this is a result of Anton and Matt Forman, that for every manifold of dimension, okay, let me check the how it goes. That if you consider now a manifold with dimension n, then it is known that, so this is Forman-Gorodetsky theorem, that if you take the space of diffeos of a manifold and you endow this space with the topological conjugacy relation, then it's not Borel, but dynamically you don't put any extra assumption. It would be nice to say that the transitive diffeomorphisms are not, the set of transitive diffeomorphisms is not Borel. But we don't know that, I think. It's not Borel if the dimension of the manifold is at least 5, and I think that recently Weinar and independently Forman and Weiss claim that this is true for any dimension greater or equal than 2. 1, even 1. Okay, thanks. Sorry for. I might be sloppy right now with all the details, because what is happening is that there's a lot of activity in this area, and new results are coming almost, well, every month. So Benjamin Weinar updated his preprint, I think, in June. Earlier, Bopeng published some results earlier, even Natalia Gonczaruk published some results on the complexity of classification of vector fields. Right, Anton? Okay. So please, it's like it is good to know the names and look into the papers. You have some, I hope you have some appetite to go into it, and you have now some understanding what you can expect in those papers. But okay, and for the last 10 minutes, we will, and now for something completely different. So we will switch a little bit our situation, and we will talk about a situation in which we know that that actually the equivalence relation is Borel. So there's one particular setting when we have dynamics and the conjugacy relation is guaranteed to be Borel, but there are a lot of open questions. So okay, you can also check surveys written by Matt Forman and some problem lists composed during the Banff workshop, co-organized by I think by Federico, right? Or you're just attending in that meeting? Okay, so now if I fix a fixed alphabet, so this is a finite set, and if I take the space of all B infinite sequences, and if I endow it with a shift action, then I obtain a compact topological dynamical system. And if I consider all subshifts, so subsets of this shift space which are non-empty, which are closed, and which are shift invariant. Then those are actually this is more or less the same as saying that I consider expansive homeomorphisms of a zero-dimensional space. And if I introduce a notion of a topological conjugacy, which is the usual notion of topological conjugacy, then the fact that my space has this very special structure and my homeomorphisms are expansive means really that the equivalence relation given by topological conjugacy on this particular space is always Borel, because the classes are always countable. Because for every shift, this was very well explained by Tamara in her talk, that in order to define a conjugacy between two subshifts, you have to decide on the finite length window, and your function has to be of this form that it looks through the window of this size onto your sequence, and it has to decide only on the basis of the information which symbols you can see in this finite horizon, what symbol to put in the image sequence. And then you shift the window one position to the right, and then you decide what is one position to the right in your image sequence. And then you shift your sequence to the left, and you decide also about one position. And there are obviously only countably many such functions. And each conjugacy between two symbolic dynamical systems has to be of this form. So we are now in the world in which the conjugacy relation is for sure Borel. But now the theory of countable Borel equivalence relations is pretty rich in itself. It uses a little bit different techniques, more combinatorial techniques than the usual ones, but it still have the same flavor, meaning that at the very, if you look at this, you have at the picture of the complexity, you always start that the simplest relations are smooth ones. So you have identity on your counter set. So this you can think of as the identity relation on the counter set as the example of the simplest countable Borel equivalence relation. Each class has only one element. And now it is funny thing that we know the next more complicated countable Borel equivalence relation, which is this relation E1 I mentioned during my first lecture, which tells you that two sequences on the counter set are equivalent even only if they are equal up to finitely many elements. After some moment, they are equal. And this relation cannot be smooth. But of course, every smooth relation reduced to that one. And here you have a bubble, which is quite complicated, because in this bubble you can still this is like a picture of some partially ordered set. Each point in this set is an equivalence class with respect to the Borel B-reducibility of the countable Borel equivalence relations. And as a partially ordered set, this set contains a copy of the partially ordered set of all subsets of natural numbers ordered by the inclusion. So you have like a partial order preserving injection of this guy into this guy, which tells you that this blob is quite complicated. It's like it's hopelessly complicated, but it does have a maximal element. So there exists a maximal element which is called E infinity, which is the most complicated equivalence relation with countable, Borel equivalence relation with countable classes, each equivalence class countable. And this is given by the, so what you do, you start with the free group or on two elements, on actually any non-trivial free group will do, and you let it act by a shift on the space of all 0, 1 configurations over the free group. So this is a classical generalization of the usual shift, that whenever you have a countable group, you can imagine that you label elements of these groups by 0s and 1s, and then you let the group act on itself, shifting elements, which shifts your labeling accordingly. So elements of this space, of course, are functions from the group to the set of 0s and 1s. So those are elements. And if you act by an element H on such a sequence, then as a result, you get a sequence like this. So this is the shift action. And as I told you somewhere there, whenever you have a group acting on the space, then you have an orbit equivalence relation. So orbit equivalence relation divides the space of all possible 0, 1 configurations over the free group into some countable equivalence classes, because each orbit is now countable. And this is the most complicated countable Borel equivalence relation, in the sense that so this is E infinity is orbit equivalence of this action. And it is known that every countable Borel equivalence relation has to Borel reduce to that maximal one. And if you can reduce this maximal one to your favorite countable Borel equivalence relation, that your countable Borel equivalence relation is as well maximal. And it is known that the topological conjugacy relation on the space of all subshifts, but without taking care for dynamics, just encoding complexity of the equivalence relation given by the E infinity, this is the result of Clemens. We know that this is maximal, but then take any non-trivial, take any family of shifts with a non-trivial dynamics. If you take the family of shifts with non-trivial dynamics, say transitive or minimal, then we don't know if it is maximal. It is open. We can only say that it is known that minimal subshifts the topological conjugacy on minimal subshift is not smooth, which means that it can be this, or somewhere here, or here, but we don't know exactly. And this is a result of Sabog and Tsankov, yeah, I should. Now I realize that I should also here mention the Kamerlo and Gauss result, who did something about complexity of minimal counter systems, not minimal, of counter systems up to topological conjugacy. But okay, let's go back here. So minimal subshift is not smooth. This is Sabog and Tsankov. And funny thing is that many years ago, Rufus Bowen kept a notebook in which he wrote down some open problems. And one of the problem 32 on this list of Rufus Bowen was classify subshifts with the specification property. I don't have time to explain what is the classification property, but now we have a partial solution to that problem, which tells that the classification of shift with specification is somewhere here, so it is above E1 even, and this is our joint work with my joint work with again Deka, Bopeng, and Marcin Sabok. And the story goes on and on and on, but I have no time. So thank you very much for your attention. And
any questions?
yeah, Kurt wants to.
Just to understand where this fits in with some other dynamical contexts.
If you give me a dynamical system, you can introduce the equivalence relation of 2 points being in the same orbit. Is that E1, though the one directly above smooth at the bottom of this bubble?
For compact systems, yes.
Yes.
Yes, I think yes, because non-trivial recurrence kills any smoothness for Z actions.
And does Dye's theorem fit anywhere into this context? Can you reinterpret it through this equivalence relation? That any dynamical system has the same sort of
No. So
equivalence relation?
Dye's theorem tells you that if you have a measure-preserving action of a countable group, then all those actions are measurably orbit equivalent. So this means that actually this is the very simple equivalence relation, right? It's all of them are in one equivalence class.
No, but I mean, for each dynamical system, you can look at the same orbit of equivalence relation.
Oh no. So then I don't think so, right? Because, but in the sense of the family of all measure-preserving dynamical systems, as a family, and the measure-preserving actions of countable groups, this is one. The complexity for topological actions is unknown, and I'm pretty sure for Z actions, the continuous orbit equivalence relation is more complex. So it is always something like that. But yeah, I don't know if this is a satisfying answer, but this is what I know.
More questions? So, if there are no questions, let's thank Dominik for all his courses.
Thank you.